Hello and welcome to our IROS 2020 presentation. My name is Maciej Bednarczyk, and I will give you an insight into our work entitled Passivity Filter for Variable Impedance Control. In modern robotics, the interactions between the robots, the environment, and human operators are not only allowed but also encouraged. This is done by the use of dedicated robotic solutions such as cobots for collaborative robots, but also by developing standard safety requirements and designing performant interaction control strategies. Among them, the most popular consists in controlling the compliance of the interaction by the means of impedance control. To do so, a mass spring damper system behavior is imposed, such as the robot is attracted to some reference position and reacts to unmodeled external forces. In this strategy, the challenge consists in guaranteeing interaction passivity, especially when modifying the interaction dynamics. It's considered the case where the desired impedance model is given in terms of time variable stiffness and damping profiles. The dynamics of the interaction between the robot and some external forces are then characterized by the controlled inertia, stiffness, and damping. In classical passivity analysis, a storage function V1 can be defined. Note that the positive function V1 corresponds to the system energy as it consists of the kinetic energy together with the spring potential energy. By computing its derivative, one can observe that the condition .V1 less or equal to the cross product between the velocity r and the external force is only ensured for a constant on decreasing stiffness profile. Satisfying this inequality is essential in order to be able to conclude on the system passivity, which is not possible here for any increasing stiffness profile. This is a major drawback for many applications where a general variable impedance control strategy is required. To overcome that issue, several strategies are proposed. The first one is based on energy tanks that allow to store and re-inject dissipated energy to modify the impedance dynamics. This strategy has found usage in many applications despite some difficulties in the tuning of the time parameters. Also, it can only be applied online during execution of the task. Alternatively, a method based on passivity conditions was introduced. This method allows to check whether a given impedance profile guarantees passivity. It uses a modified version V2 of the storage function. The conditions on V2 and its derivative result in passivity are expressed in terms of the impedance parameters. This method allows both online and offline verification, but can only be used to check passivity, but no solution is given in how to modify a non-passive impedance profile. In our work, a strategy based on the passivity condition is presented, which can also check the passivity of a profile, but also be able to modify a non-passive profile. In our design strategy for passivity filters, we consider that the stiffness and damping profiles vary according to some switching variable gamma between some minimal and maximum values. Gamma is defined as a diagonal matrix with eigenvalues between 0 and 1, and only the case where the stiffness is increasing is considered. As the other cases, passivity is always guaranteed. Additionally, as the controlled impedance model parameters are used, the user-defined, M, K, and D are considered to be chosen diagonal, what allows to decouple the impedance behavior. In this case, the passivity condition presented previously can be expressed in scalar form and reformulated in an inequality on .gamma I. Using this new condition, a passivity filter can be designed as a combination of passivity conditions with an adaptation law on the switching variable gamma I. The proposed filter allows to guarantee passivity, however, its performance highly depends on the conservatism of the storage function used to derive the passivity conditions. For this reason, we were interested in modifying the storage function in research of less conservative conditions. The resulting storage function proposed in our work is defined by V4 together with the corresponding passivity conditions. As previously, the decoupling leads to two scalar inequalities on .gamma I, and a new passivity filter can then be designed, this time with two passivity conditions. In order to test the proposed strategy, a simulation was done on a simple 1 degree of freedom mass ring damper system following a sinusoidal reference under impedance control, with a virtual mass of 10 kilograms and with a stiffness varying between 2 and 22 Newton per meters. Both passivity filters were used for comparison, and the resulting switching variable evolution shows that the filter resulting from the condition based on the proposed storage function V4, in orange here, allows a much more rapid convergence of the switching variable to the desired reference. Also, we show that using the blue switching profile resulting from the conditions of the state-of-the-art storage function V2, both functions V2 and V4 can be used to conclude on the system passivity. However, if using the orange switching profile resulting from the storage function proposed, the blue storage function V2 is too conservative to conclude on passivity. Finally, the proposed method was implemented on an experimental setup featuring a KUKA IWA robot. The performed task is a medical needle insertion into a 4-layer phantom where the layers simulate the human body biological tissues. The passivity filter is then used to modify the needle impedance profiles to better interact with the different tissues and account for their varying stiffnesses. For example, when operating outside the phantom, we wish that the robot has a lower stiffness should an unexpected contact occur, whereas the stiffness should be higher when performing a rather rigid skin layer. As it can be observed, the switch results in a smooth motion of the needle. Also, it can be seen on the right side that the high increase in the stiffness from 1000 Nm to 3500 Nm that occur when passing from the outside of the phantom into the skin layer is modified by the passivity filter, as speed of the switching variable is bounded by the passivity condition. It has been shown how to design passivity filters for variable impedance control that allow to track some desired impedance profiles while guaranteeing passivity, and the proposed method was validated in a needle insertion task using a KUKA IWA robot. Current work and future perspective consist in searching other even less conservative passivity guarantees, but also in investigating how to extend our design method to impedance model that cannot be decoupled. Thank you for your attention, and I hope to answer all of your questions and discuss our method very soon.